Okay, guys, so today we're going to look at section 3.5, or the polarity of molecules. These are the outcomes. It's actually pretty easy, and we'll end off today here at, we won't get into it, but I'll kind of introduce it, sketching these shapes using the Vesper theory. Now, when you guys did lab 6, you used computer software, but I'm going to show you how to do it without the computer software. So a polar bond is when one atom is more electronegative than the other atoms in a covalent bond. Now, these numbers you do not need to memorize. If you recall, the periodic table has a lot of information. So actually, let me just open up the periodic table to show you. Oh, it was already open. That's convenient. So hold on, guys. Let me just share that with you. Share my new screen. This is obviously your periodic table, and you can see I already have it circled here. Let me kind of clean this up. This was from the last class. Your electronegativities are, I didn't do a very good job erasing, but they're in the top left corner. The bigger the number, the larger the electronegativity, the more it's attracted to electrons. And what happens in a polar bond, so say I had a bond between fluorine over here on the right of the periodic table and like carbon, because the electronegativity is different, it would be a polar bond. Polar meaning the fluorine is pulling the negative electrons closer, and it creates a dipole or a difference, kind of like how a magnet works. There's like a north and south pole. Well, in some molecules, there's a negative side and a positive side. And we're going to look at that right now. Oops. So in this bond between hydrogen and fluorine, the electrons are over here. This means partially negative. It's not the same as an ionic bond. Ionic bonds, the difference in electronegativity is so strong that the electron actually gets transferred. But remember, in covalent bonds between nonmetals, they share, they don't transfer. So what happens is basically an unequal sharing. So the electrons would be over here, mostly on the right, on the fluorine. So a polar bond is when one atom is more electronegative than the other. But that's not really what I want to talk about today. What I want to talk about today is what makes a molecule polar. And there are 3 rules to help you guys figure out if a molecule is polar. Now, on your second test, which will be around the end of November, so a month away, you guys might get a molecule and it will be like multiple choice or true or false, is this molecule polar? And I'm going to show you how. The definition of a polar molecule is when in the entire molecule, the electrons are not shared equally. Okay, so how do we know that? How will we figure this out? Well, there's 3 rules you guys need to remember. These rules are kind of new to me, by the way. When I learned this in university and I taught it for the first few years, I used like a more complicated set of rules. But after working here for so long and working with other instructors, I've kind of we've used these 3 simple rules, and it's actually probably the easiest way I've seen this explained. So 3 rules. Rule number 1, if the molecule has 3 or more different elements, it is polar, or it could be polar. Remember, they have to have a difference of electronegativities, and we're going to practice this today. So anybody confused right now, don't worry, we will practice this today. I think I have 4 examples. So molecules are polar if there are 3 or more elements in that molecule, but they have to be different. So look at this molecule on the right. We'll start with this guy. This is CH4. We call that methane. or the British call it methane because they're crazy people. I'm only kidding. But you guys, if you had like a British school system, or maybe even in like the Middle East or anywhere outside of North America, they might call it methane. But I know in Canada and the United States, we say methane. Same thing. Some of you might be thinking, hang on, this has 5 elements. It has 1 carbon and 4 hydrogens, but they need to be different. So this molecule, not polar, it only has 2 elements. This molecule over here has 3 elements. It has hydrogen, carbon, and chlorine. So this would be I guess I would say CHCl3. Okay, so yeah, anyways, and we'll practice this, but it has 3 different elements, which means the electrons will not be shared equally. The whole idea here is if the electrons are all shared around the molecule equally, it's not polar. If the electrons are not shared equally, it becomes polar. This will mean a lot more for anybody in chemistry 2 or chemistry 3. So, engineers or some medical science students, because knowing if something is polar versus nonpolar determines its solubility, meaning does mix? So kind of an important topic, especially in oil and gas. All right, well, and again, that's not really for this course, but if any of you are wondering why this is important, for anybody moving on to do more chemistries, this is very important. Okay, so what's rule number 2? Rule number 2 is the easiest, well, one of the easiest rules. If the central atom has lone pairs, it's probably polar. So again, we have methane. This is the same molecule as before. The carbon here has no lone pairs. Remember what a lone pair is. A lone pair is electrons on the central atom that are not bonded. So they're leftover electrons. And water is a very good example of this. Water is one of the most famously polar molecules on Earth. I mean, it is. Water is a polar substance, which is why it doesn't mix with oil, which is nonpolar. So I've mentioned this before, but if you guys are bored, you could go to your kitchen right now and see this. You just take water and mix it with a bit of cooking oil, olive oil, canola oil, ghee, whatever. It doesn't matter, any type of oil, it will not mix. And that's because water is polar and the oil is not polar. So they kind of repel, or they're not attracted to each other. They don't mix. It's pretty cool. And again, you can see this in your kitchen. Okay, so rule number 1, just going to go back. If there's 3 or more different elements in the molecule, it's polar. Rule number 2, if your central atom, key word here, central atom, has lone pairs, it's polar. And rule number 3, or the last rule, is if there isn't a central atom, meaning it's just 2 elements bonded together, well, if the elements are different, it's polar. Again, remember, polar means the electrons are not shared equally. If the molecules are the same, they're going to share it equally. Shared equally. Right? So I don't know if you guys know the term tug of war. Tug of war is like a game you would play where people would pull on a rope. And usually, well, not usually, in a tug of war, when 2 groups are pulling on the same rope, the stronger group will win the contest. It pulls stronger. If the 2 groups are exactly the same, nothing will happen. They will be shared. The forces will be equal. But if you have a tug of war and you have different elements, like fluorine and hydrogen, fluorine is much stronger than hydrogen. It has a much higher electronegativity. So this would be polar because the fluorine with an electronegativity of 4 would beat hydrogen with an electronegativity of 2.1. And guys, these numbers, I don't have memorized. You do not need to memorize them. They are on your periodic table. Okay, so now, that might sound a little complicated. Let's look and let me show you how easy this actually can be. The challenge here, maybe I'll do this one and you guys can try these two. I might change one thing though. Just give me 1 second. Sorry, I just stopped sharing for 1 second. I just want to change one of the examples for you because one of the examples we've already done. So let me try this one. Okay, I'll show you what I changed in a second. Let me share my screen again. All right, let me show you too. Now, the first thing you need to do is to draw the electron dot diagram. The electron dot diagram is really important because you need to see what the central atom is, are there lone pairs, things like that. For the first two examples, I picked pretty easy ones. I know that rule number 1 is not going to apply here. None of these molecules have 3 different elements. A has just carbon and oxygen. B has just hydrogen and fluorine. So rule number 1 won't work. I'm going to need to look at rule 2 or rule 3. So let's start with the easy one, B. HF. Now, this is just more of a review for you guys on how to do the electron dot diagrams. Hydrogen is in group 1, fluorine is in group 17 or 7A. So we have 1 electron and 7 electrons. And I mean, this, you couldn't get a match better than this. We have hydrogen, we have fluorine, we have 1 electron to be shared with each of them. So the molecule would look like this. Oh, I think there's a question in the chat there. I'll get to it after I draw this shape. Okay, now let me just check the chat. Okay, yeah, so there's an answer in the chat. And you're correct, it is definitely polar. Now, how do we know that this is polar? Well, this we will use, rule 3. I can't use rule 2. Now, again, this is what really confuses students sometimes. They're like, well, there are lone pairs on the central atom, but center means in the middle. There is no central atom here. It's just 2 atoms bonded together. If you stick 2 things together, neither of them are in the middle. So we will use rule 3 here. And rule 3 says if the atoms are different, it's polar. So the answer, which I've seen in the chat already, is polar, and this is totally polar. Okay, we've already kind of looked at this example anyways. Hydrogen has an electronegativity of 2.1. Fluorine has an electronegativity of 4. This is definitely a polar molecule. The fluorine is really pulling on all those electrons. All right, let me just see the chat again. I'm getting more messages here. Abdullah in the chat says same elements, no central atom. Is that polar too? And the answer there is no. If these were the same elements, so imagine if I gave you this molecule on a test, F2. Well, F2 would look like this. I hate drawing all these dots, but anyways. There is no central atom, and this is non-polar. Again, the whole idea here is, are the electrons shared differently? And the answer is no, in the top one. In the top one, we have fluorine and fluorine, the exact same element, the same electronegativities. This would not be a polar bond. We need to have a difference in electronegativities. Okay, let's look at another one. I have worksheets on this, by the way, if you guys wish to practice. They're all online, but let's look at the next one. All right. Okay, let me pick another color. This one's a little harder in the sense that CO2 is a challenging molecule to draw, but let's have a look at this. So carbon has 4 valence electrons. Oxygen has 6. I know this because oxygen is in group 6 or 16, and carbon is in group 4 or 14. 4A we would call it, but on your periodic table it says 14. I kind of already mentioned that, Iman, but I'll come back to that in 1 second. Iman in the chat says, what about the bonds? And I'll come back to that, but yes, I did kind of mention that the bonds were polar, but I will come back to that, I promise. So I'll do the bond part in a second. So are these molecules polar? The second one is definitely polar. We'll talk about the bonds in 1 second. All right, so let's get this one done. What color do I want to pick? You know what? No, I'm not going to do that. I was going to use black. I don't think I've ever used black. I'll go light blue. Now, there's 2 oxygens, so think about how this would work. These electrons would come together to bond. Like, remember, the single electrons will always be bonded to something. So these 2 will be bonded. But remember, there's 2 oxygens. So what this molecule would look like, and I'm not spending too much time on this because we've actually drawn this molecule before in another class. So if you are really struggling with this, you might want to go back and look at other notes, because we did CO2 maybe last week. Oops, I was going so good, guys. I almost had it perfect. Okay, so that is the electron dot diagram for CO2. Now, let's ask ourselves the 3 questions. Are there more than 3 elements in this compound? No. So rule number 1 doesn't work. There's only 2 elements here, carbon and oxygen. Okay, let's go to rule 2. Are there lone pairs on the central atom? What do you guys think? Let me know in the chat. Does the central atom here, I'll give you a hint, the central atom is carbon. Does it have any lone pairs? No and no. I got a couple people saying no, and that's correct. Again, this is something that really tricks my students. Like, I can't count how many times I've been walking around the gym in the final exam, and students put their hand up and they're like, oh, are these central atoms? Or when I'm marking a test, students say, oh, this has lots of lots of lone pairs, right? They think these are lone pairs on the central atom. They are not. They are the central atom is what we look at. This central atom, it has 2 bonds. It has 2 double bonds, but it has no lone pairs. Okay, so let me just go back and ask ourselves the 3 questions. Are there more than 3 different elements? No. Are there lone pairs on the central atom? No. And then rule 3, if there is no central atom, well, that doesn't apply here. There is definitely a central atom. So the answer to all my questions is no. That means non-polar. And that's a really good way to think about this question. Think of your answer yes or no. If it's no, as in N, if your answer to all 3 questions is no, it's not polar. It's a good kind of way to memorize that or think about that. Okay, now the next question. Iman asked this, and it was kind of my fault because I never really emphasized this. Are the bonds polar? Well, let's see. In order to do that, we need to look at the periodic table, And we need to find the electronegativities of all of these elements. So let's go down to the bottom one. I'm erasing this now. The bond here between these two is between hydrogen that has 2.1 and fluorine that has 4.0. This means because the electronegativity is so different, the bonds are polar. Okay, so this is a polar molecule with polar bonds. Okay, what about the next one? Now, I had to pull up my periodic table here because I don't know this off the top. I used to. Years ago, I knew all of these electronegativities in my head, but then they stuck me in math for a while and I lost my superpowers. You know, if they say if you don't use it, you lose it, and that's so true. All right, so oxygen. The electronegativity for oxygen is 3.4. Just going to erase that. The electronegativity on carbon is 2.6. Again, because these numbers are different, and they're different by a large amount, the bonds are polar. So it does have polar bonds. And isn't that interesting? You can have a molecule where the bonds are polar, but the molecule itself is not. It's kind of a really interesting thing to think about. And again, if it was just carbon and oxygen, 1 and 1, it would be polar. But because it's a molecule, the bonds are shared equally, the electrons are shared equally. So this is a non-polar molecule with polar bonds. All right. This still might be a little confusing, but what I would like to do is for you guys to try these two, and I'll give you 5 minutes for this because it will take some time. Iman mentions in the chat, since there are 2 oxygens, does that mean we have to do it twice? No, no, no. And Abdul Halim is doing the same thing. Don't multiply, don't change the number of oxygens. I'm only looking at the bond between oxygen and carbon. Sorry, so again, what the students are saying in the chat is, why don't we multiply this by 2? We're only looking at one bond. We're looking at this bond. So don't change your numbers. Never multiply or change your electronegativities. We're just looking at one bond. All right. So why don't you guys try these two? These are good. This one we've kind of seen in the notes. D is a little new. So I'd like for you guys to try these 2 questions. So try these. I'm going to mute myself and I'll be back in maybe 3 or 4 minutes. I said 5, but maybe it'll probably only take you 3 or 4 minutes. Okay. If you do not have a periodic table with you, you still should be able to answer question 1. Okay, if you don't have a periodic table, you might not be able to do question 2. But anyways, I'll stop talking and I'll be back in a couple minutes to check all of your answers. So let's look at this. Now, I got some answers in the chat now, so let's see if you guys are correct in the chat. Step number 1 for this question is to obviously draw the molecule. So very quickly, I'll sketch these molecules. Let me pick up a different color here. Okay, so molecule number 1 looks like this, CF4. So I'm going to draw the electron dots. You could just draw a bond if you wanted, but I have a carbon bonded to 4 fluorines. Okay, so this will just take me a minute. Okay, oops, I didn't mean to put that line there. Okay, so this is carbon tetrafluoride. Not the best looking molecule I could have drawn, but the two questions are these molecules polar and are the bonds polar? So again, we're going to ask ourselves three questions. Question number one, are there more than three different elements on this atom? And the answer is no. Question number two, so that's a no. Question number two, are there lone pairs on the central atom? That's also no. The central atom, every pair of electrons are bonded. They're bonds. You don't even, I mean, a lot of times you can just draw the bonds as lines like this. That might help you understand this. There's no lone pairs on that carbon. Every electron on that carbon is bonded to another fluorine. So question number one, we have no. Question number two, we have no. And question number three, if there's only two elements in a line, question number three is if there is no central atom, well, that's not true. There's definitely a central atom. So none of these questions apply. This means it's non-polar molecule. Now, the next question was, are the bonds between carbon and fluorine polar? Now, I do not care about that there's four fluorines. That is irrelevant. I'm only trying to figure out, is the bond between carbon and fluorine polar? So carbon's electronegativity is 2.6. Fluorine's electronegativity is 4.0. This is definitely a polar bond. But even though the bonds are polar, the molecule cancels out. The molecule is not polar. Okay, now, before I do the next one, I'm just going to check the chat and make sure I'm not missing anything. Okay, just some more answers. Good. And yeah, I'm seeing lots of right answers in there from Shadan and Bader and Abdulhalim. So let's look at letter D. All right, I'll pick a new color. D is a good one, by the way. Good question. So P, phosphorus. I'll do this one a little slower. Phosphorus is in group 5. So phosphorus, or in group 15, looks like this. Hydrogen, of course, looks like this. This is a pretty straightforward molecule to draw. Every hydrogen will be bonded to, and I'll pick a different color for hydrogen. Every hydrogen will be bonded to the phosphorus. Okay, so let's go through our list of questions again. Question number 1, are there 3 different elements? No. Question number 2, is there a lone pair on the central atom? Absolutely, there's a lone pair on the central atom. There it is. That's a horrible color, isn't it? Let me pick a different color. This is a lone pair on the central atom. So this is a polar molecule. All right. What about the next question? Are the bonds polar? This is a really interesting question. Are the bonds polar? All right, let's pick purple. Well, I'm looking at the bond between phosphorus and hydrogen. Phosphorus's electronegativity is 2.2. Hydrogen's electronegativity is also 2.2. These are the same number. And even though phosphorus and hydrogen are not the same element, not even close, right? One is atomic number 15, one is atomic number 1. Even though they're not the same molecule, the electronegativities are the exact same. So the bonds here are not polar. Now, again, some of you might be thinking, well, hold up. If the bonds aren't polar, then how is the molecule polar? And it's because of the lone pair. That lone pair really makes the sharing not be equal. There's like a gap up at the top of this molecule. So again, a lot of you might think, well, if the bonds aren't polar, how could this be possibly a polar molecule? And that lone pair makes the sharing not equal. Pretty cool question. I like that question. That'd be a good test question or something. What would basically most of the electrons will be kind of dispersed around. It's kind of a hard way to explain this. Lone pairs tend to take up bigger space. This is like a little bit more complicated than you guys need to know, but the size of a lone pair, the electrons here take up more space and they will push these bonds down that way. So it's not so much who takes the electrons, it's how are all of the electrons shared, and they're not shared equally. There's like a space or a gap up at the top of this molecule because of the lone pair. Not something you guys need to know for this course, don't worry. We don't get into bond angles too much, luckily for you guys. Okay, so I'm pretty much done for today. All I want to do is introduce the next section just to get you guys a little bit caught up to the other class. And that's it. So if you just give me like 2 minutes just to introduce what we're going to do tomorrow, and that'll be it for today. All right, so putting this all together, there's really one big topic left, and it's this topic here. Now, this is not really a problem. This is what's called a rhetorical question, meaning we're not ready to do this yet. But this problem says, okay, if we have the electron diagram for silicon tetrafluoride, what would this look like in 3D is really what the question is saying. And you guys had a lab on this a week ago where you used computer software to tell me the shape of molecules. But what if we didn't have computer software? You know, what if you were doing this on an exam and you couldn't use a laptop or something? How would you figure this out? It's actually incredibly easy. And I'm going to kind of leave it with I'll do 2 more slides and then I'll just show you one thing quick and then we're done. So without computer software, so obviously this was drawn with a computer, but what if you only had, pen and paper? What would you do? Well, we need to consider something called the VSEPR or VSEPR theory. And we'll talk more about this tomorrow. But the theory is, on paper, there's only 2 dimensions, but in real life, there's 3 dimensions, meaning X, Y, and Z. So if you think about like a video game, I don't know if many of you play video games, but if you do, old video games like Mario, like the original Mario, Super Mario Bros., you could go left and right and jump up and down. Left, right, up, down. That's 2 dimensions. 3D games, so like modern games, you can go up and down, left and right, and you can also walk forwards and backwards towards or away from the screen or the camera. So 3 dimensions would have like left and right, so up and down, left and right, but it would also come out towards you in a 3rd dimension. Molecules are like that. I mean, obviously we exist in 3 dimensions, molecules exist in 3 dimensions. So this theory is going to help us explain, what these molecules look like in 3 dimensions without using a computer program. So this is valence shell electron pair repulsion. We'll talk more about this tomorrow. The last thing I want to show you is just, this is in your data booklet. I cannot stress enough how important it is for you guys to get your data booklets. They are outside my office still, and you can get them on the D2L. But this we're going to use tomorrow, okay, to figure out the shapes of molecules. And we'll worry about this tomorrow. I don't want to do too much today. It's already 3:18, but I just wanted to introduce this word so that tomorrow we can get right into it. And that way you guys won't be behind my other class. All right, guys, so I'm going to hit stop record. If there's any questions, let me know. Other than that, you're good to go.